Wish you all a very, very happy 2020. For all of you who are going to be writing the board examination this year, I wish you great success. I wish you that you score a centum in the math examination. Let's get started. What is the objective of today's session and the sessions that are likely to follow? The objective of this session is to basically revise on a chapter-wise basis every single chapter in the NCERT textbook. Each of these revision, we have budgeted it to take anything from 45 minutes to 1 hour. So in about 1 hour slots, you should be able to complete each of these chapters. What are we going to do? We're going to be looking at all the key concepts in each chapter. We're going to look at the theory, any formulae that might be there, shortcuts that you should know to quickly verify and ratify your answer. And then we're going to be solving certain typical questions. Not just that, the second objective of this is also that we have combed through question papers from 2016, be it sample question paper given by CBSE or actual board papers, and picked questions which are tested from the respective chapters in each of those years. So basically, we have provided you with practice of look-alike questions wherever a question of that kind has been tested in the board examination. Let's get started with the first chapter. Chapter 1, Real Numbers. There are 7 concepts that you need to know as far as this chapter goes. We'll start one by one. At the end of each of these concepts, we have tried as far as possible to mimic a question from that concept that was tested in a previous year board paper or in the sample question paper. I've also left you with the numbers of the questions that appear. For example, question number 14, question number 17, something like that. And from which year did it appear testing this concept, right? Let's get started. Let's start with the first of the concept. This is Euclid's Divisionlemma. The concept goes this way. Given positive integers a and b, there exist unique integers q and r satisfying this condition a equals bq plus r. Essentially, we take an a divided by a b, we get a quotient which is equal to q and a remainder which is equal to r. So a can be expressed as b times q, divisor into quotient plus the remainder. The most important thing is this condition. The remainder can take a value which starts all the way from 0. The remainder is 0, then the divisor is a factor of this dividend. The remainder can take values which is 1 less than the value of the divisor. For example, if b is equal to 10, if you're dividing a number, let's say 49 by 10, you'll get a quotient which is equal to 4, and the remainder can go to as large a value which is 1 less than the value of the divisor itself. So r lies between 0 and b. How is this concept actually tested when it comes to the CBSE examinations? They use this division lemma to basically find out HCF of numbers. So let's take a very simple example and run through that. The questions have explicitly stated that you can find the HCF using prime factorization too. There have been years where they've explicitly stated use Euclid's division algorithm to find the HCF of 135 and 225. We'll be solving a total of 10 questions in this video to cover these 7 topics, with which we would have covered all the kinds of questions that CBSE has earlier years, in the previous years, tested from this one single chapter. Right? Euclid's division algorithm to find the HCF of 135 and 225. We'll go about it stepwise. What we're going to do is we're going to take this larger number 225, that's step number 1, divided by 135. 135 goes once in 225, so the quotient is 1. There is going to be a remainder, and the remainder in this case is equal to 90. So step 1, we're going to write this 225 is equal to 1 times 135 plus a 90. So this resembles the division algorithm of Euclid. A is equal to b times q plus r. If the remainder is not 0, if the remainder is not equal to 0, then we go to the second step. In the second step, what we do is we pick the divisor of the first step, which is 135, and divide it by this remainder. 135 divided by 90. 90 goes once in 135. The remainder is equal to 45. Here again, the remainder is not equal to 0. So let's write this step. This is 135 is equal to 1 times 90 plus a 45. The remainder is not 0. We repeat this step. We take the divisor of this step, which is 90, and divide it by the remainder of this step, make that as a divisor. 90 divided by 45, the quotient is 2, and the remainder is 0. If it becomes 0, that's the step at which we stop. So 90 is equal to 2 times 45. What is our objective? We need to find out the HCF of these two numbers. The HCF is nothing but the divisor of the last step, the step in which your remainder became 0. So the HCF of 135 and 225 is equal to 45. Quickly summarize it in a printed form. We're using the division lemma on 225 and 135 because 225 is greater than 135. We're using 135 as a divisor. So 225 equals 135 times 1 plus 90. The remainder is not equal to 0. So going to the second step in which 135 becomes a dividend and 90 becomes a divisor. So 130 equals 90 times 1 plus 45. The remainder in this step is also not equal to 0. So we're going to repeat this recursively till we get a remainder which is equal to 0. So 90 is equal to 45 times 2 plus 0. The remainder here is 0. So the divisor of this step is the HCF, right? So you write all of these things. This could be a 2-mark or a 3-mark question. Let's check out when was this tested. This question appeared in the 2019 sample question paper given by CBSE. This is question number 13. Let's move to the second concept. This concept is the fundamental theorem of arithmetic. Fundamental theorem of arithmetic is very, very simple. It says that pick any positive integer. You can prime factorize that number in only one way. Let's say you take a number like 40. 40 can be expressed as a product of its prime factors in only one way. 40 is a 8 into 5 or a 10 into 4 or a 2 into 20. You can say multiple things. But let's say I write it as a 2 into 20. I write it as a 5 into 8, 5 into 8, whichever way I like it. This 2 into 20 can further be written as 2 into 2 into 5. This 5 into 8 can be written as 5 times 2 times 2 times 2. So the prime factorization of 40 is going to result in a unique value. That's what this fundamental theorem of arithmetic is. Every composite number can be expressed, can be factorized as a product of primes, and this factorization is unique. Apart from the order in which the prime factors occurred. Here we wrote it as 2 cube into 5. In the second one we wrote it as 5 into 2 cube. But 5 into 2 cube or 2 cube into 5 is going to be one and the same. Where is this used? They actually ask you to prime factorize numbers. Questions of that kind have appeared. 182 can be expressed as a product of its primes as follows. A similar question has appeared either in the sample question paper or in the actual exam paper. Let's quickly run through it. 182, let's prime factorize it. 182, if you know tables, it becomes quite easy. I know this number is 14 times 13, so I'll get there straight away. 14 can be written as a 2 times 7. So 2 times 7 times 13. Let's check out which answer choice matches. 2 times 7 times 13. B is the answer. This is a question which appeared in the sample question paper given in 2020, right? That's a paper in which you had these objective type questions. Prime factorized it. If what I did not appeal to you, this is a very systematic way of going about it. 182 is an even number divided by 2 gives you a 91. 91 is divisible by 7 leaves you with 13. All of these are prime numbers. So 182 equals 2 times 7 times 13. Choice B is the answer to this question. When did it appear? It appeared in both the papers. One in 20, you had a similar question in 2020 sample question paper. This is question number 4. This was a multiple choice question. In 2019 board paper, you did not have a multiple choice question, but a similar concept was tested. This is question number 4 with an internal choice 2. So prime factorization of numbers is tested. Let's move on. Third concept that we're going to be looking at is HCF of numbers. HCF of numbers, when they say without mentioning that use the Euclid's lemma to find out, find the HCF using the prime factorization method. How do you find out? Step 1, prime factorize the given numbers. Step 1, prime factorize the numbers. Step 2, HCF is the product of two things. The smallest power of each common prime factor in the numbers. Let's take an example to understand how this works. We're trying to find out the HCF of 324 and 180. Let's prime factorize both these numbers. That's step number 1. Step 1, 324, if you know tables, life is very simple. 324 is an 18 square. 18 is not prime, so we can write it as 2 times 9. That's 2 times 3 square square. 2 times 3 square square. So prime factorization of 324 is 2 square times 3 power 4. If this does not appeal to you, start with this 324 divided by 2 and run through this entire process. You'll get the answer. It's probably going to take you another 45 more seconds. But if you knew this, you saved a lot of time. Second one is we are prime factorizing 180. 180 is 20 times 9. 9 is a 3 square. 20 is a 4 times 5, which is 2 square times 5. We prime factorize both these numbers. That's step 1 done. Step 2, pick only primes which are common to both the numbers. 2 is a prime common to both the numbers. 3 is a prime common to both the numbers. The smallest power of 2 between the two numbers is a 2. So we go with 2 square. The smallest power of 3. We have a 3 square and a 3 power 4. We'll take the smallest power. So we go with a 3 square. 2 square times 3 square. The product of the smallest power of common primes is going to be the HCF. 2 square is a 4. 3 square is a 9. So the HCF of these two numbers is 36. Choice B is the answer. Quickly summarize it in a printed form. Prime factorizing the numbers. 325 prime factorizes as follows. 180 prime factorizes as 2 square times 3 square times 5. Pick the common primes. 2 and 3. In the lowest power, 2 square, 3 square. The product of that, 36, is the answer. When did this appear? We'll look at it. We'll do the LCM, HCF, LCM and HCF combination questions, and then let's look at when such questions appeared. This is a question, it's an objective type question, so it figured in one of the two sample question papers for 2020. That's a year in which they started introducing this multiple choice questions. Go on to LCM. Step 1 for LCM is the same as what we did for HCF. Prime factorize the given numbers. That's the first step. Second step, in HCF, we picked common primes. Here we are going to pick every single prime factor. In HCF, we pick the lowest power. Here we are going to pick the greatest power. So what is LCM? LCM is a product of the greatest power of every single prime factor involved in the numbers. Okay, let's pick an example and quickly run through this concept. Trying to find out the LCM of 1080 and 2268. Step 1, we'll prime factorize both these numbers. Right. 1080 is quite easy to prime factorize. I know 108 is 27 into 4. So 1080 is actually equal to 27 times 40. I'm going to start with points that I know very well. 27 is a 3 cube. 40 is a 5 into 8, so 5 times 2 cube. So this number is quite easy. 2268, I'm not even going to sweat. I'm just going to go about it the typical way of dividing it by a 2. 2 is the smallest prime that I know that will divide it. So it makes it as 1134. This number is again divisible by 2. 1100 by 2 is a 550. 550 plus 17, 567 is what we have. 5 plus 6, 11 plus 7, 18. This is divisible by 3. So this number is divisible by 3. 567 by 3. This is 18 times, that's a 27. 189 is what we have. This number is again divisible by 3. Let me divide it by 3. I'm left with the 63. This is again divisible by 3. I'm left with the 21. This is again divisible by 3. I'm left with the 7. So 2268 prime factorization. Wherever you can go about it this way, you save time. If you're quickly not able to find out what it is, just don't take any longer. Then just quickly run through this process. It takes you probably another 30 seconds to get to the answer. So 2268 is equal to 2 square times 1234, 3 raised to the power of 4 times 7. We need to find out the LCM. Step 2 will give us the LCM. Step 2, LCM is a product of all different primes you see. What are all the primes we are seeing? 2 is a prime in both these numbers, 3 is a prime in both these numbers, 5 is in the first number, 7 is in the second number. So written down all the primes. Pick them in their highest power. The power of 2 between these two numbers, 2 square, 2 cube, I'm going to go with the 2 cube. That's the greatest power. 3 cube and 3 power 4, so I'm going with 3 power 4. 5 power 1, 7 power 1. So these are the numbers that we have. So product of this should give us the answer. Let's quickly run through what we have. 2 cube into 5, which is an 8 into 5, 40 times 81 times 7. 40 into 80 is a 3200. 40 into 81 is a 3240 times 7. That's what we have. 3000 into 7 is a 21,000. So that part is done. 240 into 7 is 1680. So the answer is 22680. So LCM of these two numbers is 22,680. Quickly summarize it in a printed form as we run through this process. Prime factorize both these numbers. Prime factorizes as 2 cube times 3 cube times 5. This one took a little longer for us. 2 square times 3 power 4 times 7. Picking all the prime factors, all the prime numbers 2, 3, 5, 7. Respective highest power 2 cube and 3 power 4. 5 power 1, 7 power 1. The product is equal to 22680. Choice D is the answer. This question also appeared as part of one of the sample question papers. Right? It's not HCF of 32 and 46. It's actually LCM of 1080 and 2268. Let's move on to the next one. This concept is the concept where it basically reads this way. Product of any two positive integers, A and B. If you know that, A times B will be equal to the product of the HCF of AB and the LCM of AB. One very important thing to keep in mind. This need not necessarily hold good once you go beyond two numbers. A into B into C need not be equal to LCM of ABC and HCF of ABC, right? Obviously, CBSE is never going to test this way. I'm just giving it to you as an extra thing. So in case in future, when you write any of the entrance examinations, once you go to 12th standard and later on, don't use this formula and extrapolate it saying that it worked for two numbers, it might work for more than two numbers. It will not necessarily work for more than two numbers. For two numbers, product of the two numbers is equal to the product of the LCM of those two numbers into HCF of those two numbers. Let's take a question as it appeared in one of these papers that we had combed through. Here is it, that find the HCF of these two numbers, 32 and 46. You need to find the HCF of these two numbers. Step 2, you need to verify that the product of the LCM and HCF of these two numbers is the same as the product of these two numbers. Let's start by prime factorizing 32. It's a very easy number to prime factorize. 32 is equal to 2 raised to the power of 5. 46 is equal to 2 times 23. That's again a very easy number to prime factorize. What's the HCF of these two numbers? pick the common prime. The only common prime is 2 in its lowest power, that's 2 power 1. HCF done. Let's move on to the LCM. LCM, write down all the primes, only 2 primes, so 2 and 23. Highest power of 2 is a 2 power 5 times 23 should give us an answer. 32 times 23 is the answer. 32 into 20 is a 640. 32 into 3 is a 96. So the answer is equal to 736. We have found out the LCM, we have found out the HCF, both parts done. Let's find out the product of the LCM and HCF. LCM times HCF is equal to 736 times 2, which is 1472. Now let's verify whether that's the same as the product of these two numbers. The product of these two numbers is actually a 32 times 46. 46 into 30. 46 into 30 is a 1380. 2 into 46 is a 92. So that's equal to 1472. Right. Just take 1 minute to see why it works. See, when you find the product of these two numbers, we're multiplying these three numbers. 2 power 5 into 2 into 23 in the prime factorized fashion. That's 32 into 46. This is what your right hand side was. The left hand side, what did you do? You took 2 power 5 and 23 as the LCM. That's your LCM. Your HCF was a 2. You're still multiplying the same three numbers. So LHS should be equal to RHS. So product of any two numbers will always be equal to the product of the LCM of those two numbers and the HCF of those two numbers. Quickly summarize it in a printed form. We're going to prime factorize the numbers. Quite easy numbers to prime factorize. LCM, HCF is picking the only common prime in its lowest power, which is 2. Finding the LCM is picking all the primes in the greatest power, which is 2 power 5 into 23, which is 736. Now comes the verification. Taking the product of the LCM and HCF, which is 1472. The product of the two numbers is also 1472. So this should give you the mark that you're looking at. This is the proof that we had to do. Let's move on to the next one. These questions are what I would call as word problems. You get questions of this kind where you need to figure out whether it's an LCM question or a HCF question. Obviously, no one is going to point out to you that it's a HCF question this way in the exam. Let's quickly run through this question. Find the largest number which on dividing 31, 62 and 75 leaves remainders of 1, 2 and 3 respectively. Got a number, let's say that number is equal to n. I'm dividing 31 by n. The remainder I'm getting is equal to 1. I'm dividing 62 by n. The remainder of this division is equal to 2. We'll write it here. I'm dividing 75 by n. The remainder of this division is equal to 3. So look at it. If 31 leaves you a remainder of 1, for example, I divide 7 by 6, I get a remainder of 1. If I divide 6 by 6, the remainder is going to be equal to 0. So if I subtract 1 from it, that number should be divisible, right? So if I subtract 1 from 31, the balance 30 is a number that will be divisible by n. I'll also walk you through this through another step when we go to the next slide. But right now think about it this way. 7 when it was divided by 6, we got a remainder of 1. The remainder 1 is you have 1 more extra. Subtract that 1 from 7, the balance will be divisible by 6. That's what I'm doing it here. 31 minus 1 is divisible by n. 62 when it was divided by n, we got a remainder which is equal to 2. So if I subtract 2 from it, that value 60 should be divisible by n. Extending the logic here, 75 was divisible when divided by n, left as a remainder of 3. So if I remove this remainder 3 from 75, 72 is a number that should be divisible by n. So n divides 30, n divides 60, n divides 72, which means n is a number that's a factor of all of these things. If it could divide all of these numbers, it's a factor of 30, it's a factor of 60, and it's a factor of 72. The question is asking us to find out the largest such number, which means that the n that we are trying to find out is the HCF of these three numbers, 30, 60, and 72. It's a word problem because you had to deduce that this largest number is the HCF. That's where the crux of solving this question is. Beyond this, it's very simple mechanics. Step 1, let's basically prime factorize given numbers. 30 is 6 into 5, which is 2 times 3 times 5. 60 is equal to 12, twice this. So we'll go with the 2 times 30, which is 2 square, 2 times 2, 2 square times 3 times 5. 72 is equal to 8 into 9. So 8 is a 2 cube, 9 is a 3 square. HCF is the product of common primes. 2, 3, 5, 2, 3, 5, 2, 3. So we're going to pick the common primes, which are 2, 1, 3. Lowest power of 2 between these numbers is basically a 2 power 1. The lowest power of 3 among the three numbers is basically a 3 power 1. So HCF is equal to 2 power 1 into 3 power 1, which is equal to 6. The largest number that can divide 31, 31 by 6, look at it, the remainder is 1. 62 by 6, the remainder is 2. 75 by 6, the remainder is 3. So it satisfies this condition, and it's incidentally the largest number. Quickly run through it. I said I'll explain this a little differently in the slide. I'm going to do that here. 31, if let's say that number instead of D, I think we've gone to the capital N here, let N be the largest number which satisfies this condition. So 31 is equal to A times N plus 1. This is actually applying nothing but the division lemma of Euclid. Pick 31 divided by N, get a quotient a remainder of 1. Run it through for the next two numbers. 62 is equal to some other multiple of N, B times N. The quotient is going to be different. The remainder is equal to 2. 75 is equal to C times N plus 3. I'm going to take this 1 to the left hand side. That will leave us with 30 is equal to A times N. I'm going to take the 2 to the left hand side. That will leave us with 60 is equal to B times N. Whatever I said, the second method is this. Take the 3 to the left hand side. That will leave you with 72 is equal to C times N. Now look at it. 30 is some multiple of N. 60 is some other multiple of N. 72 is some other multiple of N, which means N will divide all these numbers. N is going to be a factor of all of these numbers. And if N is the largest number that can satisfy this condition that we are looking at, N has to be the HCF of these three numbers. Prime factorize these numbers. Pick the common primes, which are 2 and 3 in the lowest part. Find the product, 6. 6 is the answer that we are looking at. Let's move to the next one. This is an even more interesting question. Here again, it's a word problem. I didn't want to tell you whether it's a HCF problem or an LCM problem. Let's figure out along the way. 6 different sweet varieties of count. Various numbers are given. Let's not worry about it right now. They're ordered for an occasion. They need to be packed in such a way that each box has only one variety of sweets. For example, let's say this is Rasagulla and this is Gulab Jamun, right? So if a box contain Rasagullas, it will contain only Rasagullas. You cannot mix sweets of different varieties in a box. That's a condition given. And the number of sweets in each box is the same. If box number 1 had 5, then box number 2 will also have 5. Box number 105 will also have 5. Every single box will have the same number of sweets. What is the minimum number of boxes required to pack it? Let's say in each box, we're going to throw in n sweets. So 32 is broken down into n sweets. And let's say we need a such boxes. So 32 is going to be equal to a times n. So there are n sweets going into the box. We need a such boxes to pack 32 sweets. It comes to 216. That box is also going to contain the same n number of sweets. But because we have a larger number of sweets here, the number of boxes that you'll require is going to be a different one. It's not going to be A, it's going to be a B. Quickly run through this. 136, number of sweets in the boxes n will require C boxes. Let's go for 88 is equal to n sweets in the box will require D boxes. 184 sweets will have n sweets in a box will require E number of boxes. And for 120, we'll have n sweets in the box and will require F number of boxes. As we did in the last question, n is a multiple of 32. 32 is a multiple of n. 216 is a multiple of n. 136 is a multiple of n. 88 is a multiple of n. 184 and 120 are also multiples of n, which means n is a factor of all of these numbers. N will divide all of these numbers. So n is a factor of all of these numbers. Now hold on for a minute. This 32 sweets, can I pack it as 4 sweets, number of sweets in a box and the number of boxes? 4 into 8 is a possibility. I can do 16 sweets in a box and have 2 boxes. I can pack 32 sweets in a box and have 1 box. As the number of sweets in the box increases, the number of boxes will go down. That's evident. We are looking for the minimum number of boxes, which means we need to find however many, what is the largest number of sweets that can go into each of these boxes. We realized n is a factor of all of these numbers. Now we need n to be as high a value as possible. N is a common factor to these numbers. If n takes its highest value, then n is equal to the HCF of all of these numbers. 32, 216, 136, 88, 184 and 120. We are not finding out n. N is a number of sweets in a box. What we are finally going to find out is the number of boxes. We'll come to that in a while. We'll first compute the number of sweets. Consolidate till this point in a printed form. All sweets need to be packed and each box has only one variety and all boxes contain the same number of sweets, which means that the number of sweets in each of the boxes is the HCF of all of these different values. Next step, let's find out the HCF. Let's start by prime factorizing these numbers. 32 prime factorizes as 2 power 5. 216 is a 6 cube. 6 is a 2 into 3. So 216 becomes 2 cube times 3 cube. Wherever something is not evident, just run through it this way. Pick this 216 divided by 2 and run through the successive division. Where you know the answer, just go with it. 136. 136 is equal to 17 times 8. If you know your tables, it's going to be super easy for you. 88 is quite evident as 11 into 8, which is 11 times 2 cube. 184. 160 is divisible by 8. 184 should be divisible by 8, which is equal to 8 times 23, which is 2 cube times 23. Lastly, 120, certainly divisible by 8, which is 15 times 8, 15 times 2 cube. So prime factorized all these numbers. HCF is the product of the common primes. What are all the common primes? Is a 2 here, 2 here, 2, 2, 2. 2 is the only common prime among all of these numbers. 2 power 5, 2 cube, 2 cube, 2 cube, 2 cube, 2 cube. The lowest power of 2 among these numbers is a 3. So 2 cube is a HCF, 8 is a HCF. What did we say was a HCF? HCF was the number of sweets in each of the n is equal to the HCF of all of these numbers, which works out to 8. So in each box, we're going to be packing 8 sweets. We need to find out the minimum number of boxes. You can go about it 2 ways. I'll do it one way in this slide, and I'll do it in a slightly different fashion in the next slide. I'm going to count out the number of boxes, right? We're having 8 sweets to a box. 32 sweets of the first variety are there. So 32 gets packed into 4 boxes. Now I'm counting the number of boxes. Second one, 216. How many boxes? If I remove this 8 from it, I'll have 27 boxes. 136 is equal to 8 times 17. 8 sweets go into it. How many boxes do I require? I require 17 boxes. 88, 8 sweets in a box. That will leave us with 11. We'll require 11 boxes. 184, we will require 23 boxes. And 120, we'll require 15 boxes. Add all these 6 numbers. We have the answer. 31 plus 17, 48 plus 11, 59 plus 23, 82 plus 15. 97 boxes is what we'll require. The minimum number of boxes required to satisfy all of this is 97. Watch out, finding the HCF is not just enough. HCF tells you the number of sweets in the box. What we have to find out is the number of boxes. There's a slightly different approach to get to this answer. We'll quickly run through it. Finding the HCF is definitely a step that we can't escape. We have prime factorized this. We have found out the HCF. HCF works out to 8. Now, all I'm going to do is I'm going to count all of these sweets. Find out the total number. There's a total number of sweets I have. I'm packing 8 sweets to a box. All that I'll have to be careful is that I just put the same type of sweets in a box. So all of these total count divided by 8 is going to give me the number of boxes required. This is the number of sweets. They add up to 776. I divide 776 by 8. I have 8 sweets going into a box. We'll find out what this number is. 77 by 8, that's going to leave me with a 972, 56, that's going to be a 7. Probably a quicker way to doing it is, this is 800 minus 24. 800 is 100 times 8. 24 is 3 times 8. So 100 minus 3 would have given you the same 97. So number of boxes required is equal to 97. This is clearly a HCF question. A difficult question would have been a 4-mark question if such a question were tested. Let's move on. Let's check out when all was the concept of LCM and HCF tested. Look at it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 questions we have been able to comb from papers from 2018 to the sample paper given in 2020. So LCM, HCF, the concept of LCM times HCF is a product of 2 numbers, and word problems involving LCM and HCF are often tested. This is a concept where you need to have a good handle about it. Let's move to the next one. It's a concept about irrational numbers. Let's define what irrational number is, and we'll also look at how the decimal expansion of an irrational number is. This is the last but one concept. A number S is called an irrational number if it cannot be written in the form P by Q, where P and Q are integers and Q is not equal to 0. Rational number will say can be written in the form P by Q. Irrational number is something which cannot be written in the form P by Q. Standard questions get tested quite often testing this idea. Second one, how will an irrational number look in its decimal expansion? An irrational number in its decimal form is going to be non-terminating. It's going to be infinite, and it is going to be non-recurring. Just give you an example of a number like this. It could be 0.11121314, and they'll leave you with these dots saying that it is non-terminating. And look at the pattern. It's not repeating. It's not 1111. It's not 121212. It's 11121314. This is an irrational number. This is how the decimal expansion of an irrational number is going to appear. Let's get started with the questions that tested both these ideas. Start with the first one. This is a classic question, gets tested quite often. Prove that some number is irrational given that this is irrational. So I'm going to walk you through the steps literally orally, and then we'll look at it in a printed form. we'll start by assuming the contrary. We'll say that 6 plus root 7 is rational. If you're saying that this is rational, we have said that in the first part, a p by q is not the form in which an irrational number can be written. A rational number is something that can be written in the form p by q. So we'll write it as an a by b. So 6 plus root 7, if it is rational, they are saying prove it is irrational, we are assuming it to be the contrary. So if 6 plus root 7 is rational, it can be expressed as an a by b, where a and b are co-prime integers and b is not equal to 0. So therefore, I can write this root 7 as a upon b minus 6. We'll rewrite it as a minus 6b upon b. A and b are co-prime integers. 6 is an integer. So a minus 6b will be an integer upon an integer. This value is a rational number, which boils down to saying that if a minus 6b by b is rational, root 7 is rational. But we know, and the question is explicitly stated, that root 7 is irrational. Why do we have this contradicting answer? That's because of our incorrect assumption that 6 plus root 7 is rational. That's how you prove that 6 plus root 7 is irrational. I'm going to quickly walk you through how you should write this in the examination. It will exactly state this. We are going to assume the contrary, that 6 plus root 7 is rational. We are actually trying to prove this. We are assuming the opposite. If this is rational, then we can express it as an a by b. This gets rewritten as a minus 6b by b is equal to root 7. A minus 6b by b is rational, which means root 7 has to be rational. But this contradicts what we know, that root 7 is an irrational number. Why is that? Because of our incorrect assumption. If our assumption is incorrect, what is the correct thing? The correct thing is that 6 plus root 7 is an irrational number. So if I write all of these steps, you will get 2 or 3 marks. This is usually tested as a 2-mark question or as a 3-mark question. It's more of the next idea that's tested in the irrational number. This appeared in the sample question paper. Which of the following is a decimal expansion of an irrational number? What is the concept for irrational number decimal expansion? It has to satisfy 2 conditions. 1, it should be non-terminating, which is it should be infinite. 2, it should be non-recurring. These are the 2 conditions that it should satisfy. Excuse my handwriting, it's right. 3.201, it's terminating, so it cannot be an irrational number. 0.67 with a line on top, with a bar on top, which essentially means that this number is 0.676767. It is non-terminating, good, but it is recurring, so it's obviously not an irrational number. 9.23, let's quickly finish it. This is a terminating decimal, cannot be an irrational number. Look at this number, 6.1. These dot dot dots say that it is non-terminating. Let's see if the pattern is repeating. 02, 002, 0002. So which means that it is non-recurring. So this is the number which is an irrational number. It's a 1-mark multiple choice question that appeared in the sample question paper. Quickly run through this. The definition of the decimal expansion, how will it be? It's going to be 1, non-recurring, and it is going to be infinite or non-terminating. 3.201 is terminating, so therefore it is not rational. Let's look at the second one, which is 0.67 with a bar on top, which means that this number is recurring. It's non-terminating, but it is recurring, therefore it is not an irrational number. Third one, it is 1, non-terminating, and it is also non-recurring. So this is the irrational number in the group. The next one is a terminating decimal, therefore it is not irrational. Choice C is the answer to this question. Where did these questions appear? Testing this concept of prove that this is irrational and the decimal expansion appeared so many times. 1, 2, 3, and then there are another 4 more questions. 7 questions appeared from 2016 onwards testing this idea. So this again is an important idea where you need to have a good handle on it. Let's look at the last of the concepts, revisiting rational numbers and their decimal expansion and the fact whether they are terminating decimals. Start with the first one. If x is a rational number which terminates something like 4.54 or something, then when x can be expressed in the form p by q. It's obviously a rational number, so it can be expressed in the form p by q, where p and q are co-prime, such that the prime factorization of q will be of the form 2 power n into 5 power m. When you take the denominator and prime factorize it, the only prime factors that it will have will be 2 or 5. It will not contain any other prime factor. That's what it says. Where m and n are non-negative integers. The converse is also true. If it's a terminating decimal, it can be expressed in such a way that q will have only 2 or 5 as prime factors. The second part, it says that let x be equal to p by q be a rational number such that the prime factorization of q leads to us to this form 2 power n and 5 power m. Then it will be a terminating decimal. If it's a terminating decimal, this is how its denominator is going to be. If you realize its denominator to be of this form, then it will be a terminating decimal. So the vice versa, the reverse also holds good, is what is the second point. What if it does not hold good? If the prime factorization of the denominator is not of the form 2 power n 5 power m. For example, let me take a number like, let's pick something like 11 upon 21. Q is the denominator here. Let's prime factorize it. This becomes 3 times 7. So the denominator when prime factorized is not of the form 2 power n 5 power m. So this number is going to be a non-terminating decimal. Quickly run through it. It is recurring, non-terminating. That's the most important. We are trying to find out whether it's terminating, whether it's finite. It's going to be a 4.52 or it is going to be 8.3333. That's what we are trying to find out. Quickly run through a question that tested this idea. The decimal representation of this number will terminate after how many decimal places? They've asked this. If, look at the denominator comprises only 2's and 5's, which means it's certainly going to be a terminating decimal, no doubt at all. To find out how many decimal places will it end with, will it terminate with, the way to go about it is basically take this denominator and ensure that the powers of 2 and 5 are the same. Let's do that. Here the power of 2 is a 2, the power of 5 is a 1. So I need to make the power of 5 also as 2. So we already have a 5. Let me multiply it with one more 5. I multiplied the denominator with a 5. To retain the validity of this number, not to change the number, I need to multiply the numerator also with a 5. So both these 5's will get cancelled to leave us with the original number. But what it does to us is 23 times 5, which is 115. Let's keep that in abeyance for a moment. Let's not worry about it. The denominator becomes 2 square times 5 square. 2 square times 5 square is nothing but 2 into 5 the whole square, which is equal to 100. 115 by 100. Shift the decimal places 2 to the left. That's going to be 1.15. So how many decimal places will it terminate? It's going to terminate after 2 decimal places. The idea is to make the denominator a power of 10. How do we make it? You can make it only when the powers of 2 and 5 are the same. Quickly run through this in a printed form. To find the number of decimal places after which a fraction will terminate, first and foremost, you need to ensure that the denominator comprises only 2's and 5's. Otherwise, it's not going to be terminating. Make the powers of 2 and 5 in the denominator the same by multiplying and dividing the fraction by an appropriate number. What we have here is the power of 2 is 2, the power of 5 is 1. We need to make the power of 5 also as a 2. So multiply and divide this expression by a 5. Once you do that, you get 115 upon 2 square, which is 1.15. It's going to terminate after 2 decimal places. If you have a 10 power 7, it will terminate after 7 decimal places. That's what it is. Whatever is the power of 10 that you find is the number of decimal places after which it's going to terminate. Choice B is the answer to this question. Let's quickly check out when was this tested. This idea of rational numbers, the terminating decimal, and the number of decimal places after which it will terminate has been tested 4 times between 2019 and 20 sample paper and the board paper. So again, this is an important concept that you need to know. Quickly run through all of these. Pick the book, NCERT book. Whatever I've taught is again there. Pick 1 or 2 exercise questions. Summarize it. It will take you another 1 hour to run through this process. Once you're done that, you can put a tick mark for chapter number 1. Are we going to go through this revision till the examination? Yes, we are going to be doing it. When are we meeting next? We're meeting at 7 p.m. on Monday, February 3rd, 2020. This is to look at the topic polynomials. Where can I catch these videos? At youtube.com/Maxtute. Tell your friends, classmates to watch this. So in this duration, each week we are targeting to do 2 chapters as revision. So by the time you head into March 12th, which is when your board examination is, we should have gone through all of these revisions thoroughly. Best wishes. Before you go, I want you to do one thing. I want you to sign up at this particular URL. This is going to be a URL that's going to appear here, which is online.maxtute.com. All the revision lessons that I'm doing are going to be uploaded there. So even at a later time, you can go through it. It's got slide packs. It's got some more extra questions for you to practice. So hit a centum. See you on the next session. Best wishes.